All right, I want to talk you through number 41 and 42. I know I mentioned only 42, but I'll talk you through both of them just to show you how they compare it. All right, what we're looking at here is you want to know the total delta HF for the entire process. And sodium chloride is pretty straightforward compared to the lithium fluoride that was in the notes and that was in the book. So if you think about the order of it, the first thing that you'd have to do, or that I always end up doing, is subliming the sodium. And so the enthalpy of sublimation for sodium, the first step that you're going to have for this one would be the sodium solid going to sodium gas, and that's contribution would be 109 kilojoules. Okay, now once we have it to gaseous sodium, we've got to turn it into an ion, and so we need to take neutral sodium and we need to remove an electron with the process of ionization energy, and that's going to be right here, which is going to be 495 kilojoules per mole. Okay, again, these numbers are given to you on these, nothing that you have to do on your own. All right, so now sodium ion is good. So now what I need to do is I need to end up taking my chlorine and cutting it in half. But here is one of the tricky parts, is that for chlorine, it gives me the bond energy, for the entire single bonded diatomic chlorine, but I only need half of it. So in order to do that, I only need 1/2 of the chlorine atom. So I need to take that bond energy, which is 239, and divide it by 2. Okay, so that's going to be that contribution for chlorine. And then the last part is to take the chlorine first and make it into an ion, which is going to be taking, I should probably keep my states here just so that you know what we've got. Gaseous chlorine, adding an electron, which is going to be electron affinity, and getting it to the chlorine ion in the gaseous state. That delta H is right here, which is negative 349 kilojoules. Then last but not least, I've got the lattice energy, which is taking the sodium ion, adding it to in its gaseous state, adding it to the chlorine ion in its gaseous state, getting sodium chloride solid. That's a total of negative 786. And then to get the answer to this, all I have to do is add all of those together, and that's going to give me a final answer for delta H formation. Remember, that's just at standard conditions. I'm really going to crunch here, I apologize that. Negative 412 kilojoules. Wow, that's bad. Oh, it's going to let me, no. And so that right here is negative, I know it's tough to see, negative 412 kilojoules is what that says there. All right, now if another page, okay, now let's do 42, because 42, the process is very similar, but I want you to understand some of the other curveballs. So let me show you those. All right, now 42, the only thing that's different here is we're going to take magnesium solid, add it to fluorine gas, and get magnesium fluoride solid. But we've got some imbalance of charges here because magnesium's a 2+ and fluoride is a 1-. So the first step is still going to be to sublime magnesium. Okay, so I'm going to take magnesium solid, get it to magnesium gas, and probably use my parentheses, and that's going to be 150. Not sure why that's disappearing. Notice excuse me, it's got the decimal place for significant figure purposes. Alright, to form the magnesium ion, we have to remove 2 electrons. And that's why you have the first ionization energy of magnesium. So you'd have magnesium gas. You would be removing the first electron. Not sure why this is disappearing. And that first ionization energy is 735 kilojoules. Now as soon as we remove that first electron, all the protons are going to pull magnesium a little bit closer. So to remove the second electron, the energy is going to go up. So now we've got magnesium 1+. We're removing a second electron to get it to magnesium 2+. And you'll notice that the ionization energy went up, which we've noticed before, or we've noticed in patterns before, 1,445 kilojoules for the second ionization energy. All right, now for fluorine, okay, so magnesium is where we want it. It's a gas and it's an ion. For fluorine, it gave us the bond energy of fluorine. Now up here for number 41, we cut the bond energy in half because we only needed 1/2 of the chlorine molecule. Well, for the fluorine, we need both particles of fluorine because it's MgF2. So for fluorine, we're going to keep the bond energy intact because we need 2 fluorides separated, and it's already a gas. So we're going to keep that the same. So the bond energy we're going to keep is 154. We're not going to cut it in half like we did with the chlorine gas. Okay, now we need to generate excuse me, fluorine ions. So for the fluorine ions, okay, since there's 2 of them, we need to add 2 electrons to get 2 fluoride ions, which means that we have to take that electron affinity and multiply it by 2. So 2 times negative 328. Not sure why they're disappearing. And then lastly, so now we've got our gaseous fluoride ion, we've got our gaseous magnesium ion, that's a 2 plus there, not 2 minus. Now I've got my ionization energy. So I have magnesium 2 plus being added to 2 fluorides, which are each a 1 minus. They're both in the gaseous state. We're going to get 1 formula unit of magnesium fluoride solid, and that is going to release negative 300, well, it's going to release 3,916 kilojoules, and since it's releasing it, it's exothermic. And if we add all that up, we get a delta H formation. Let's see if I can't fit this in here. Okay, our delta H formation is going to be equal to negative 2,088 kilojoules per mole. Okay, and it's per 1 mole because we're dealing with 1 mole of magnesium fluoride. Okay, so there's 41 and 42. Hope that helps. Let me know if you have any more